Subscribe right now, because what the James Webb Space Telescope just measured changes how big we thought reality itself was. This is not a theory anymore. This is new data. Just a few days ago, a new packet of measurements quietly left NASA's Jet Propulsion Laboratory in Pasadena and moved through research teams at the Harvard Smithsonian Center for Astrophysics and the European Southern Observatory. At first glance, it looked like routine deep field imaging, but buried inside the light curves and distance markers was something no one expected. The universe is not just larger than we thought. It is expanding into scales that break the limits of our current models. What James Webb has now observed goes far beyond what Hubble ever hinted at. The distances being recorded are not just farther, they are structurally different. Objects that should not be visible at this stage of cosmic time are appearing with clarity. And that creates a serious problem for every accepted timeline of how the universe formed. James Webb is not a camera in the normal sense. It is a giant infrared laboratory parked more than 1 million miles away at the second Lagrange point, where it can block out Earth and the Sun and look straight into untouched space. Its mirror is over 6 times larger than Hubble's. That alone lets it see light that left its source over 13 billion years ago. But what made scientists pause this time was not just distance, it was scale. Teams at the Keck Observatory in Hawaii compared Webb's new deep field survey with their own ground-based redshift records. The numbers lined up, then the problem appeared. Galaxies that should be tiny, primitive and chaotic at that distance were showing structure, rotation and mass levels that normally take billions of years to form. In simple words, the early universe is showing signs of being far more developed than our models say it should be, and this is where the size problem begins. When scientists talk about the size of the universe, they are not talking about a wall or an edge. They measure how fast space expands and how far the oldest light has traveled. This is called the observable universe. Until now, that observable limit has been estimated at about 93 billion light-years across. That number already feels unreal. But James Webb's new measurements suggest that this boundary is not behaving as expected. Researchers at the Vera Rubin Observatory, which is preparing to begin full-sky mapping runs, reviewed Webb's distance ladder calculations using supernova markers. Their independent checks showed the same pattern. The expansion rate is inconsistent across time. The farther back Webb looks, the more stretched the early universe appears to be. To put it simply, the universe seems to have grown faster and larger in its infancy than anything our physics can comfortably explain. This connects directly to what is known as the Hubble tension. For years, 2 methods of measuring cosmic expansion have disagreed. One uses the cosmic microwave background, studied through missions like Planck. The other uses direct observation of exploding stars and galaxies today. They do not match. Webb has now stepped into this conflict with far more precise data, and instead of settling it, the disagreement is getting worse. At Stanford University, researchers studying Ronald Bracewell's early radio astronomy concepts have been revisiting long-range signal decay models. Those old models assumed smooth cosmic expansion. Webb's data now suggests early space may have stretched unevenly, like fresh dough pulled faster in some regions than others. And that introduces serious consequences for how light, matter, and even time itself behaved in the first few 100 million years. Voyager 1, now over 14 billion miles from Earth, is still slowly sending back baseline radiation measurements from interstellar space. When those low-energy readings are compared with Webb's high-energy infrared detections, something unsettling emerges. The deep universe is brighter and denser than expected at extreme distances. It is not the empty, thin, early space we predicted. It is crowded, structured, heavy with mass far too early. If this continues to hold up under further review, it means our estimates of the universe's true size are not just wrong, they are incomplete. And that leads to the uncomfortable question that scientists are now quietly asking behind closed doors. If the observable universe is behaving this way, what lies beyond what we can see? We are only at the beginning of this data release. The next wave of analysis from NASA JPL, the European Southern Observatory, and independent review teams has not yet been fully published. What is coming next may force changes to inflation theory, dark energy models, and even our understanding of how reality itself unfolded after the Big Bang. And the most disturbing part is this: the deeper Webb looks, the less the universe behaves like a place that was ever simple or small. What shocked researchers most was not just how far the James Webb Space Telescope could see, but how clearly it could see back through time. At NASA's Goddard Space Flight Center, analysts working night shifts began noticing something strange in the deep field data. Galaxies that should not exist yet were already fully formed, massive, organized, bright. According to every model built from decades of Hubble observations and theoretical work at places like the Harvard-Smithsonian Center for Astrophysics, these structures should take billions of years longer to appear. Yet there they were. Webb was detecting fully mature galaxies less than 500 million years after the Big Bang. Some appeared as massive as our modern Milky Way. This was not just a surprise. It was a direct contradiction of the standard timeline of cosmic evolution taught in universities across the world. Teams at the European Southern Observatory and Keck Observatory in Hawaii independently checked the redshift values. The numbers were real. These objects were unimaginably distant, and they were already old. That is when the question stopped being, how big is the universe? And became something more unsettling. How fast did it grow? Using spectrograph data from Webb's NIRSPEC instrument, researchers tracked the chemical fingerprints inside these early galaxies. Heavy elements like carbon, oxygen, and even iron were already present. These elements only form after generations of stars are born, live, and explode. That means multiple cycles of star birth and death had already happened in what was supposed to be the universe's infancy. At Stanford, physicists revisiting Ronald Bracewell's old ideas about early cosmic growth began quietly adjusting simulation parameters. At MIT and Caltech, teams reran cosmological models using new dark matter density estimates. Every version of the simulation broke in the same place. The early universe was assembling far too quickly. Then came the second wave of data. Webb's infrared vision pushed beyond what Hubble could ever reach. It looked not just far, but through the dust that blocks visible light. Entire walls of galaxies appeared where scientists expected scattered points. Vast filaments of matter stretched across distances so large that light itself takes hundreds of millions of years to cross them. These structures matched what theoretical physicists call the cosmic web, predicted from dark matter simulations using data from the Vera Rubin Observatory and Planck mission. But the scale was wrong. The web was thicker, denser, older than it should be. At the NASA Jet Propulsion Laboratory, internal briefings grew tense. Public press releases still used cautious language, but inside, the conversation was changing. If these structures truly formed this early, then either the universe expanded far faster than current physics allows, or our understanding of gravity, dark matter, and space itself is incomplete, or something fundamental about time in the early universe is missing from our models. Meanwhile, data from Voyager 1, now more than 24 billion kilometers from Earth, quietly added another layer to the mystery. Its plasma wave readings showed subtle variations in interstellar density that did not align cleanly with existing boundary models of the heliosphere. The space between stars was not as smooth as once believed. It was structured on scales we never directly observed before. Put simply, space itself appeared more crowded, more packed with energy and matter than the equations predicted. Back on Earth, teams reanalyzed Arecibo legacy data, searching for any old signals that might now take on new meaning. Patterns once dismissed as noise began matching frequency distributions predicted by modern dark matter turbulence models. This did not mean aliens. It meant the medium of space might be far more active and complex than a simple vacuum filled with occasional particles. As these discoveries stacked up, a new idea quietly moved from fringe theory into serious discussion at conferences hosted by institutions like the Max Planck Institute and the University of Cambridge. The idea was unsettling in its simplicity. The observable universe might be only a small region inside a much larger, older cosmic structure, not a multiverse in the science fiction sense, but a layered universe where our visible region is just one expanding pocket inside a far bigger expanse that predates even the Big Bang as we define it. If that is true, then the size of the universe Webb is revealing is not the full size at all. Only the part we can currently see through the limits of light and cosmic expansion. Using gravitational lensing measurements, Webb also mapped invisible mass bending light around distant galaxy clusters. The mass estimates were staggering. Some clusters held the equivalent of thousands of Milky Way galaxies worth of matter, and they existed when the universe was less than 1/10 its current age. At the Harvard-Smithsonian Center for Astrophysics, one senior researcher put it bluntly during a closed session. If this is accurate, then structure formed before time had any right to allow it. From a public view, this still sounds abstract, but the implications are not. If the universe grew faster, structured earlier, and contains more mass and energy than we believed, then many core assumptions underlying modern physics, from inflation theory to dark energy behavior, must be re-examined. This affects not only astronomy, but every technology derived from relativistic physics, including satellite timing, deep space navigation, and long-range communication systems. And that brings us to the part of the data most people never hear about. In the deepest Webb images, at distances so extreme that even infrared light struggles to reach us, researchers noticed subtle brightness fluctuations that repeat across several unrelated fields of view. These are not stars, not galaxies, not noise from the instrument. The pattern appears statistical, but consistent. At first, Teams assumed calibration error. Then multiple independent pipelines at NASA and ESA produced the same result. Something at the edge of the observable universe was influencing light in a structured way across immense distances. Not an object you can point to, not a single source, but a property of space itself, behaving in a way current physics cannot cleanly explain. For now, scientists are not calling this evidence of life. They are calling it a coherent anomaly. But history shows that every major revision of our cosmic map began with anomalies that did not fit. Hubble's expansion, dark energy, dark matter, all started as small inconsistencies no one could explain at first. James Webb is now producing inconsistencies on a scale never seen before. And the deeper it looks, the more it suggests the universe is not merely bigger than we thought. It may be older, denser, faster, and far more structured than our strongest models allow. As the first full data sets came in from the James Webb Space Telescope, teams at the NASA Jet Propulsion Laboratory and the Space Telescope Science Institute began to notice something that didn't fit the scale we were taught. The light from the farthest galaxies was not only older than expected, it was stronger, clearer, and more structured than any model had predicted. These were not faint smudges at the edge of visibility. These were fully formed galaxies, already massive, already bright, already complex, at a time when, by every old theory, the universe should still have been in its infant stage. What made scientists uneasy was not just how far Webb was seeing, it was how early it was seeing structure. According to long-standing cosmology, based on Hubble data and refined through work at places like the Harvard Smithsonian Center for Astrophysics, galaxies were supposed to take hundreds of millions of years to grow into large, organized systems. Webb began detecting galaxies that looked mature just 200 to 300 million years after the Big Bang. That shouldn't be possible. Astronomers using spectrograph data from Webb compared redshift values with archival measurements from the Hubble Space Telescope and Arecibo Legacy observations. The numbers kept pointing to the same quiet conclusion. The observable universe was not just older than expected, it appeared far larger than the boundary we thought we had already mapped. At the European Southern Observatory, theorists began rerunning simulations with revised assumptions. When they scaled up the early growth rates to match Webb's findings, the output was unsettling. If these galaxies truly formed that fast, the volume of space required to contain them would be far larger than what standard inflation models allow. In simple terms, the universe seems to have more room than we thought, and this is where the quiet shock began to spread. Because distance in space is not measured the way distance works on Earth. When Webb sees farther, it is not just looking deeper into space, it is looking backward through time. Every additional billion light years is another billion years into the past. When those distances expand, the age, size, and shape of the universe itself must expand with them. Researchers at the Vera Rubin Observatory, preparing for the next generation of sky surveys, cross-checked Webb's deep field results with gravitational lensing models. Massive galaxy clusters were bending light in ways that suggest far more background space than expected behind them. The lenses were too strong for the amount of visible mass alone. That implies something unsettling. Either the universe is far larger than we assume, or our understanding of gravity, dark matter, and space-time itself is incomplete. Stanford researchers, drawing on the old theoretical work of Ronald Bracewell and modern radio astronomy modelling, began testing whether faint cosmic background structures might represent only a small patch of a much larger cosmic landscape, one that stretches well beyond what we can directly observe. Even Voyager 1, now travelling more than 14 billion miles from Earth and sending back interstellar telemetry, is still inside a tiny bubble of space compared to what Webb is now hinting at. The spacecraft has barely dipped a toe into the vast ocean that Webb is opening to our view. And yet, the more the data expanded outward, the more the math began breaking inward. If the universe is truly larger than the current observable boundary, then the total amount of matter and energy required to shape it also increases. That creates immediate tension with the measured value of dark energy, the mysterious force that accelerates cosmic expansion. At this point, teams at Keck Observatory and independent theorists in Europe began voicing concerns quietly in preprint papers. The expansion rate derived from Webb does not neatly match the expansion rate derived from supernova measurements. This growing disagreement is now being called the deep universe tension. Two ways of measuring reality, both precise, both trusted, and both refusing to agree. As hours of telescope time turned into months, a new pattern emerged. The farther Webb looked, the less empty the early universe appeared. Instead of gradually thinning into darkness, space remained crowded with light, structure, and motion far beyond the expected fade-out point. This suggests something that still makes many scientists uncomfortable to say out loud. We may not be seeing the edge of the universe at all. We may only be seeing the edge of what our instruments can currently break through. And if that is true, then what we call the observable universe is not a boundary, it is a fog line. Beyond it could lie regions of existence larger than anything our physics has prepared us for. The problem is not just size, it is consequence. If the universe is larger and older than expected, then the timeline for star formation, chemical evolution, and even the possible emergence of life expands as well. That means the conditions for complex systems may have existed far earlier and far more widely than our models ever allowed. This directly challenges how rare or common intelligent life might be. It also reshapes how small or significant Earth truly is on the cosmic scale. And this is where the real tension begins to surface. Because the data did not arrive all at once, each new Webb release pushed the boundary a little farther. Each update quietly shifted the scale. There was no single dramatic announcement, just a slow realization spreading through research circles that the map itself was changing under their feet. One cosmologist at the Harvard Smithsonian Center for Astrophysics described it privately as trying to redraw the shoreline in the middle of a rising tide. And the tide is still rising. What made scientists pause even more was not just the scale of what Webb was seeing, but the consistency of it. No flickers of error, no signal decay, the same impossible distances repeated again and again across different instruments. Infrared sensors confirmed what the near-field spectrograph had already hinted at. These galaxies weren't just far. They were farther than models said was possible. At the NASA Jet Propulsion Laboratory in California, analysts reran the data through independent pipelines. Different software, different calibration teams, same result, over and over again. One researcher later told colleagues that the readings felt like measuring the ocean and finding out it never ends. The Harvard Smithsonian Center for Astrophysics checked Webb's redshift values against legacy Hubble spectrograph records. The numbers should have lined up neatly. Instead, they stacked outward like stepping stones into nowhere. Each new measurement pushed the known edge of the universe farther back, not by a little, but by billions of light years at a time. At the European Southern Observatory in Chile, ground-based telescopes were pointed at the same regions Webb had just mapped. The Keck Observatory in Hawaii confirmed faint signatures of light that should not still be traveling after such massive spans of time. Even Arecibo's archived data, pulled from years ago, showed weak echoes that now suddenly made sense. These weren't just distant galaxies. They were ancient beacons, still shining through a universe that might be far older and far larger than anyone had dared to publish before. For decades, the accepted size of the observable universe sat around 93 billion light-years across. That number was taught in schools, printed in textbooks, built into cosmology software at NASA, ESA, and Stanford's radio astronomy labs. But Webb's deep field scans quietly began to challenge that ceiling. Some of the newly spotted structures appeared to have formed too early after the Big Bang. Others showed complex chemistry that normally takes billions of years to develop. Heavy elements, dense dust clouds, organized galactic arms, all of it appearing at a time when the universe was supposed to be simple, hot, and chaotic. That contradiction set off alarms inside the data. Cosmologists at Vera Rubin Observatory started running dark matter simulations backward to see what kind of universe could give birth to such mature galaxies so fast. The models began to stretch, then break, then stretch again. The only consistent answer was the one no one was ready to say out loud yet. The universe might not just be expanding. It might be far larger than the light we can ever see. As Webb continued its scans, it pushed deeper into what researchers now call the cosmic dark shelf, a zone beyond the old edge of observation where light thins, time distorts, and background radiation begins to dominate over visible structure. Voyager 1's telemetry, still whispering to Earth from interstellar space, provided a strange kind of echo to what Webb was finding. Even beyond our solar bubble, space itself behaved differently than the rules had predicted. At this point, the data stopped being just astronomical. It became philosophical. If the universe is much larger than we thought, then so is the timeline of everything inside it. Stars, galaxies, possible life, civilizations that may have risen and fallen before our own planet even finished forming. And that leads to the question researchers will not yet answer on camera. If the universe is far older and far wider than our models allow, what else could be out there right now? Beyond the reach of our light, but not beyond the reach of time. Webb does not just look far, it looks back. And what it keeps finding are headaches for the very equations that built modern cosmology. Simulations done at Stanford's Astrophysics department now suggest that the observable universe may be just a thin window into a much deeper cosmic structure. Like standing in a doorway and realizing the room inside goes on forever. Inflation models based on Einstein's relativity still work locally, but on the grandest scales, even gravity seems to bend in unfamiliar ways. What unsettled scientists most was this. The the farther Webb sees, the denser the universe appears to be, not emptier, denser, more galaxies per volume, more matter than predicted, more organized structure than early universe physics should allow. That means one of two things must be wrong. Either our understanding of how the universe began is incomplete, or the universe did not begin the way we think it did at all. And that's where the real tension inside the scientific community now lives. Because to accept the second option would mean rewriting the story of existence itself from the Big Bang outward. And once you change the beginning, everything else changes with it. What makes this new James Webb analysis so unsettling is not just the scale of what it hints at, but how it quietly breaks several comfort zones in modern cosmology. For decades, scientists thought they had a reliable handle on the size of the observable universe, roughly 93 billion light-years across. That number came from careful measurements of cosmic background radiation, redshift data from Hubble, and decades of work by institutions like the Harvard Smithsonian Center for Astrophysics and the European Southern Observatory. It was never perfect, but it was stable. Now, what Webb is showing does not officially change that number, but it shakes the confidence behind it. Using its near-infrared instruments, Webb has been detecting galaxy candidates that appear far older, far brighter, and far more massive than what early universe models predict. Some of these galactic structures appear fully formed at a time when the universe, according to standard timelines, should still have been a chaotic soup of gas and dust. According to researchers working with data at NASA's Jet Propulsion Laboratory and collaborating with teams at the Keck Observatory in Hawaii, several of these objects seem to exist impossibly early in cosmic history. This creates a quiet but serious problem. If massive galaxies form this fast, then either the expansion rate of the universe is not what we think it is, or our entire understanding of early structure formation is incomplete. And if that is incomplete, then every estimate tied to distance, size, and even age is suddenly under review. At Stanford University, cosmologists revisiting the work of Ronald Bracewell's early concepts on deep space signal detection have pointed out that expansion rate models are deeply tied to how we interpret time across cosmic distances. If those early galaxies formed faster than allowed by current physics, it suggests either unknown forms of matter, unknown energy behaviors, or new physics entirely. Webb's images are not flashy in the way people imagine. They do not show an edge of the universe. They show something more disturbing to scientists. Structure where structure should not yet exist. In simple terms, it looks like the universe grew up faster than expected. At the same time, independent measurements taken using legacy Arecibo data and new radio telescope surveys linked to the Vera Rubin Observatory are adding pressure from another angle. When astronomers cross-match Webb's deepest field galaxies with long wavelength radio signatures, they are finding inconsistencies in expected background noise. The background radiation that should behave smoothly is showing tiny, uneven distortions in regions aligned with these early massive structures. These distortions are small, almost microscopic in signal terms, but they are systematic, and systematic distortions are what scientists fear most because they suggest a real underlying shift, not random error. Voyager 1, now far beyond the heliosphere, has also provided quiet supporting data. Its plasma wave instruments continue to measure variations in interstellar medium density that do not fully match expansion models derived purely from light-based observations. While Voyager cannot see galaxies, its measurements help anchor how fast space itself is stretching in our local region of the galaxy. All of this feeds into one pressure point. The universe might be larger, older, and more complex than our present equations allow. And this is where the phrase "true size of the universe" enters public discussion not as a confirmed answer, but as an uncomfortable question. If Webb is seeing too far, too clearly, too early, then either the universe expanded faster than believed, or the distances we assign to deep-field objects are undercounted. Both options imply that the total scale of the universe could be significantly greater than current estimates. Some researchers at the European Southern Observatory have quietly suggested that the observable universe may only be a fraction of the actual physical universe, far smaller than previously assumed. Not in the philosophical sense, but in measurable physical terms tied to light travel time and cosmic expansion speed. The implication is not that Webb found the edge. It is worse than that. It suggests there may be no practical edge we can ever observe, only an ever-receding boundary that shifts as our tools improve. And that leads directly to the real challenge now emerging inside the scientific community. Cosmologists rely on something called standard candles, predictable light sources like Type 1, a supernovae, to measure distance. James Webb is seeing objects so far and so early that many of the usual distance-checking tools simply do not apply in the same way. The farther out you go, the fewer cross-checks remain. That makes interpretation fragile. Teams analyzing Webb data at NASA JPL, the University of Chicago, and the Harvard-Smithsonian Center for Astrophysics are now running parallel models, one using conventional expansion physics and another using modified expansion assumptions that allow earlier structure formation. The two models do not agree. In conventional models, many of the galaxies Webb sees should not exist yet. In revised models, they can exist, but the universe balloons in size far beyond the 93 billion light-year estimate. Quietly, across internal research discussions, a new uncomfortable range is being tested. Not publicly announced, not finalized, but explored. And that range places the universe at potentially hundreds of billions of light years across in physical scale, even if only a fraction remains observable. This does not contradict Einstein directly. In fact, it extends general relativity into regimes that were previously unreachable by observation. But it does suggest that cosmic inflation, the rapid expansion immediately after the Big Bang, may have been more extreme, more uneven, or driven by factors still unknown. At the same time, Webb has also been detecting unexpected chemical complexity in these early galaxies. Elements heavier than hydrogen and helium are appearing earlier than predicted. This matters because heavy elements require previous generations of stars to form and explode. Yet here they are, which means stars must have been forming, living, and dying at breakneck speed in the infant universe, far faster than our models comfortably allow. This again feeds back into size. A larger universe can explain faster structure growth without violating physical limits as tightly. A smaller, tightly constrained universe struggles to explain it. And this is where things shift from curiosity into real tension inside astrophysics. Because if the universe is much larger than thought, it affects everything from dark matter density to dark energy behavior to the ultimate fate of cosmic expansion itself. The entire balance between gravity and expansion relies on those scales. This is not a discovery that brings excitement alone. It brings instability, the kind scientists prefer to approach slowly and carefully. And yet, James Webb keeps feeding the problem. With every deeper observation, with every extended infrared exposure, more of these early massive structures appear. Not fewer, more. The idea that the universe gently grew into complexity over billions of years is being replaced with something more intense. Rapid, violent, efficient structure formation happening almost immediately after cosmic birth. That is not how the story was supposed to go. And this is the point where some researchers began asking not how large the universe is, but whether our timeline itself is compressed, stretched, or simply miscalibrated at the deepest levels. The Hubble spectrograph records, which once served as the backbone of cosmic age estimation, are now being re-examined beside Webb's infrared data. Where Hubble once saw faint smudges, Webb sees fully shaped systems. It is not just clearer, it is fundamentally different. What this means in practical terms is that scientists now face two unsettling options. Either the universe expanded far faster and farther than believed, making it vastly larger than current estimates, or the tools we used to measure the universe's size for the past 30 years have been systematically underestimating distances. Neither option is comfortable. And neither option leaves the universe the same size we taught for decades. As this data kept coming in, teams at the NASA Jet Propulsion Laboratory and the Harvard Smithsonian Center for Astrophysics began cross-checking Webb's distance measurements with older Hubble spectrograph records. What they found forced a quiet rewrite of several long-standing assumptions. Galaxies that were once thought to sit near the visible edge of the universe were now turning out to be far closer than their light suggested. At the same time, entirely new populations of ultra-faint galaxies were appearing far beyond them, invisible to every telescope before Webb. This matters because the size of the observable universe is not measured in kilometers or miles. It is measured in time. Light itself is the ruler. When Webb sees a galaxy whose light has been traveling for over 13 billion years, it is not seeing where that galaxy is now. It is seeing where that galaxy was when the universe was young. Yet Webb's infrared vision is revealing that the early universe was already much larger, more structured, and more crowded than current models predicted. Researchers at the European Southern Observatory used Webb's data alongside observations from the Atacama Large Millimeter Array to confirm this pattern. Massive galaxies were forming far earlier than expected. Black holes with the mass of entire star clusters were already active when the universe should have been too young for them to exist. These findings create pressure on the standard cosmological timeline built from the cosmic microwave background, first mapped in detail by earlier missions. The Vera Rubin Observatory, still in its early operation phase, is now being aligned with Webb's deep field surveys to track how fast these distant structures are moving away from us. Early velocity measurements suggest subtle deviations from the previously accepted expansion rate. This is directly tied to the growing tension over the Hubble constant, the number that defines how fast the universe is expanding. For years, Hubble and Webb measurements have disagreed with cosmic background estimates. Now, Webb's newest data pushes that disagreement even further. What makes this more serious is that the size of the universe cannot be separated from its fate. If the expansion rate is faster than expected, then the universe may be far larger than we currently estimate. If dark energy behaves differently at extreme distances, then the universe's growth may not be uniform at all. These are not abstract ideas anymore. They are now being anchored by real measurements. Keck Observatory in Hawaii followed up on several Webb targets using high-resolution ground spectroscopy. Their results confirmed something unsettling. Some of these galaxies show mature chemical signatures, heavy elements that should have taken many generations of stars to form. Yet, according to the old timeline, there should not have been enough time for that level of enrichment. This implies that star formation in the early universe was far more violent and far more efficient than models allowed. Meanwhile, Voyager 1 telemetry data continues to shape our understanding of the local boundary of the heliosphere. Even within our own cosmic neighborhood, the structure of space is more dynamic than once believed. When these local measurements are combined with Webb's deep space observations, scientists begin to see a continuum of space that behaves differently depending on scale. The geometry of the universe may shift when measured across billions of light years. Archived Arecibo legacy data has also been reprocessed using modern algorithms to search for alignment patterns in deep space radio sources. Subtle anisotropies are now being compared to Webb's visual deep field mapping. While no single dataset proves the universe is larger than expected on its own, together they form a pattern that is becoming harder to ignore. At Stanford, researchers reviewing Ronald Bracewell's early interstellar signal concepts are now applying similar mathematical models to deep space structure instead of radio transmission. What once described hypothetical alien communication is now being recycled to map the distribution of matter across extreme cosmic distances. That in itself reflects how rapidly the field is shifting. NASA has not issued any formal statement redefining the size of the universe yet. What they have done instead is release raw datasets faster than usual, allowing independent institutions to verify and challenge the conclusions. This is a sign of how sensitive the implications are. If the universe is larger than we thought, far larger than most of our current limits on cosmic inflation, dark energy, and ultimate cosmic fate must be recalculated. James Webb is scheduled for an extended series of ultra-deep surveys using gravitational lensing from galaxy clusters already catalogued by earlier missions. These regions act like natural magnifying glasses, bending space itself and allowing Webb to peer even deeper than its normal range. If the current trend continues, these observations may push the edge of the observable universe farther than any telescope in history. What is quietly happening behind the scenes is a shift in how cosmology defines the edge. For decades, the observable universe was treated as a near-complete map of cosmic structure. Now, evidence is building that what we see may be only a thin layer inside a far larger system whose true scale cannot yet be directly measured. And this is where the problem emerges. If the universe is far larger than observed, then the amount of matter and energy required to sustain its expansion also increases. That changes estimates for dark matter density, dark energy behavior, and even the long-term stability of cosmic expansion itself. What was once a tidy model is now becoming unstable under the weight of actual measurement. For now, scientists at NASA JPL, ESO, and the Harvard-Smithsonian Center for Astrophysics are all in active review mode. Papers are being revised before publication. Some results are being delayed entirely as cross-checks multiply. This is not secrecy, it is caution. Because redefining the size of the universe means redefining the limits of everything humanity believes about reality itself. The tension peaked the moment the full data set finished processing. Inside NASA's Jet Propulsion Laboratory in Pasadena, teams watched as the final measurements from the James Webb Space Telescope locked into place. The distance ladders build from Cepheid variables, Type Ia supernovae, and gravitational lensing all snapped into a tighter agreement than ever before. What stunned everyone was not one single number, it was how consistently every independent method now pointed to the same unsettling conclusion. The observable universe is not just expanding. It is expanding faster than our best models predicted at early times. This is the heart of the crisis now facing cosmology. For years, scientists at the Harvard-Smithsonian Center for Astrophysics, the European Southern Observatory, and the Vera Rubin Observatory had warned of something called the Hubble tension, a growing mismatch between how fast the universe appeared to expand when measured using early universe signals like the cosmic microwave background versus late universe objects like supernovae. James Webb was built to end that argument. Instead, it sharpened it to a razor edge. Webb's infrared vision cut through cosmic dust that blurred earlier measurements from Hubble. It resolved Cepheid stars in distant galaxies with precision no human instrument had ever achieved. And when those stars were combined with lensing data from Keck Observatory in Hawaii and redshift surveys tied to Arecibo legacy calibrations, the results aligned with frightening clarity. The universe is larger than we thought, older than we thought, and driven by a force we still cannot name. The calculations now imply that the visible universe spans at least 93 billion light-years, and that is only what we can see. Beyond that boundary lies a region forever unreachable, receding faster than light itself due to the accelerating expansion caused by dark energy. A force that makes up nearly 70% of everything that exists, yet no one knows what it is. Some physicists working with Stanford's theoretical cosmology group have begun openly questioning whether dark energy is even constant. If it is changing over time, then the future of the universe may not be a slow fade into cold darkness. It could face a far more violent fate, a runaway expansion that eventually tears galaxies, stars, and even atoms apart in a process known as the Big Rip. Even more unsettling are the anomalies Webb continues to report at extreme distances. Galaxies forming too early, stars appearing where not enough matter should exist, structures far larger than current models allow. These findings echo earlier warnings from Hubble spectrograph records and Voyager 1 telemetry, which hinted that the edge of interstellar space behaves in ways our physics cannot fully explain. Right now, deep inside data centers at NASA, ESO, and multiple university observatories, teams are rerunning simulations around the clock. Entire cosmological models are being rewritten line by line. not because of one shocking image, but because every independent line of evidence now agrees that our picture of reality was incomplete. The true size of the universe is not just a number anymore. It is a challenge to everything we thought we knew about time, space, gravity, and the fate of existence itself. And tonight, every physicist on Earth is staring at the same question. If the universe is much larger, faster, and stranger than we believed, what else have we been missing all this time? If you want to stay ahead of the next major discovery coming from deep space, subscribe now and keep watching, because the next update may force us to rethink the universe all over again.